Welcome. After learning about the liquefaction refrigeration, now we go on to learn the applications of these processes for the natural gas processing. So, in this particular lecture, again we shall be looking at some series of this topic in the hydrocarbon recovery in natural gas systems. In this particular lecture, we shall be learning about dew pointing, the hydrocarbon recovery by propane refrigeration, stabilization and demethanizer. So, let us first see that why do we need this recovery of the hydrocarbons. Now, we know that the pipeline grade natural gas has to meet the natural gas we are going to sell, the sale gas, that has to meet some stipulated heating value, and it has been found that if there is a dilution by the nitrogen or carbon dioxide, the heating value is quite high than the stipulated value. And what we find that the presence of the various types of hydrocarbons, because any kind of hydrocarbons can be burnt, and due to the combustion of these hydrocarbons, lots of heat will be generated. So, we find that the hydrocarbon recovery is done why to lower the heating value and what we call the fuel conditioning, the condition of fuel. So, we have to take out those other hydrocarbons, so that we want only natural gas, means that methane we want in this, so that the heating value stayed within the limit. And to produce valuable liquid hydrocarbon products, means the recovered hydrocarbons are not thrown out, they are also used to make some other products. And we know there are so many products which are made from the hydrocarbons. Many kind of polymers are made, like for example PVC, which we use in our day-to-day life, that is a hydrocarbon product. So, this sort of many other products are there in our day-to-day life, that we for that we need these hydrocarbons. So, this natural gas provides a very good source of the hydrocarbons, which are the raw materials for other commercial products. And we also need this recovery of the hydrocarbons for control the dew point, or we call it dew pointing. In this way, this is necessary to reduce the liquid content in the natural gas pipelines. We know that if the higher hydrocarbons are more, then the dew point of the system will also be raised. That means we will be getting the dew point or the liquid product very easily. So, and we do not want the liquid product to be too much, because otherwise what will happen, they will accumulate in the pipelines. So, we have to recover those higher hydrocarbons, so that we can lower the dew point. And here we see that the high liquid content reduces gas throughput, causes sluggishness and interferes with gas metering. That's what I say, that if the amount of, if the natural gas has too many higher hydrocarbons, heavier hydrocarbons, then it will liquefy easily. And if it liquefies easily, what will happen? They will start blocking the pipelines, and the gas flow will be hampered. And also, we will not be able to measure the flow rates of the gas easily, because of presence of the liquid. And this is also done to avoid gas condensation due to sudden fall in the temperature or pressure if the gas is in retrograde condensation region. So, this retrograde condensation we learnt earlier. We shall again see it, recapitulate what we learnt earlier, to see that if we want to avoid this gas condensation, we do not want to go into the retrograde condensation region. So, in that case also we need to adjust the dew point, and it is less demanding than hydrocarbon recovery. Means even though it is, there are many things we are doing to do that, but this is not so costly as the recovery of the hydrocarbons. So, we generally do the dew pointing. Now, let us see at the retrograde condensation. This particular curve we saw earlier also, and as we said that this curve is very peculiar for the natural gas, and this is a typical retrograde this curve, pressure and temperature curve, that is the equilibrium curve for natural gas. And as we learnt earlier, this curve will differ for different types of natural gases depending on the composition. And here we see that here we have 3 points A, B, C, and this A is the cricodentherm, that is the highest temperature below which we will get the two-phase, and above which we will not get two-phase. Whatever which changes we can do with the pressure temperature. That means in this region, even if we keep reducing the temperature or increasing the pressure, we will not be able to get two phase. So, this is a Criquet-Dentherm, and then the B is a Criquet-Dent bar. This is the highest pressure below which we have two phase and above which we will have only single phase. Okay, and the C is a critical point we know, and we find that in these particular regions we will be having single phase, either the liquid or the vapor. Okay, only within this particular region which is given by this particular envelope, this we are getting the two phase region, and this particular dashed line, it shows the curve for a given quality, that is the amount of vapor in the total mixture. Okay. So, as the pressure drop along the vertical dashed line, liquid phase forms until the pressure is below the envelope. Okay. So, we find that this particular line, this is the, suppose at this particular temperature we are reducing the pressure, and as we know that when we reduce pressure, what happens, liquid goes into vapor state, but in this very peculiar, we find when we reduce the pressure, the vapor is going into a two phase region. That is peculiarity, and until when we keep on reducing pressure, it is there existing in the two phase region until it comes out of this envelope, and again we shall find this is the vapor we are getting. Okay. So, this is the peculiarity, and when we look at this, suppose we look Criquet-Dentherm of the 95% quality curve. Suppose this is 95% quality curve, and this Criquet-Dentherm is about 50 degree Fahrenheit, 30 degree centigrade lower than that of the original mixture. So, we find that this Criquet-Dentherm for this particular curve is lower than the Criquet-Dentherm for the 100% quality line. Okay. So, here we find this is this difference is about 30 degree centigrade, and we find that how is difference coming? Only 5% is condensing. That means a small reduction or small condensation leads to a large difference in the Criquet-Dentherm. And Criquet-Dentherm depends strongly on the molecular weight and less on the concentration. That means this Criquet-Dentherm, if we have higher hydrocarbons, that will have some Criquet-Dentherm, the lower hydrocarbons, it has another Criquet-Dentherm. It does not matter how much amount of that hydrocarbons are there, but how heavy the hydrocarbons are. And example has been given that methane containing about 10 mole% of propane has Criquet-Dentherm comparable to methane containing 0.06 mole% of heptane. So, we can easily see that heptane is much heavier than propane. Heptane is C7H16, okay, and propane is C3H8. So, that means heptane is a much heavier molecule than propane, and even if it is present in a very, very small amount and propane is at a very large amount, but the Criquet-Dentherm seems to be almost close. So, it is the molecular weight which determines the Criquet-Dentherm more than the concentration. That is why it is important for us to closely monitor the amount of the heavier hydrocarbons present in the natural gas. Now, we come to the hydrocarbon recovery processes. There are many processes that exist to recover the hydrocarbons, and the choice or the selection of the process would depend on the desired products, what kind of product we want, the amount of the gas being processed, the inlet composition of the gas, and the pressure. Okay, so these are the factors which determine the selection of a particular process for recovery of the hydrocarbons. Now, one way is that we do external refrigeration, and it is used to remove significant amount of C3 plus components. C3 plus means propane and higher components. Okay, so it is external refrigeration is used for that, and the lower gas temperatures as the gas goes into the other stage of hydrocarbon recovery. So, this by refrigeration we are lowering the gas temperature which is coming into the system, and the vapor compression is using propane is the most common. We shall be discussing about this vapor compression cycle using propane. Now, here is the typical system for the propane refrigeration system. Here I have shown that we have a compressor and we have a condenser, we have receiver, and the jetty valve is there for expansion. We have a chiller and the suction drum. So these are typically the main equipment needed to carry out this propane refrigeration, and here also we have given the sum of the values of the various temperature pressures at different points of the system. So let us see this A to B. This is a compression of the saturated vapor from about 1 bar to about 17 bar. So here we find that from here A to B we are raising the pressure from about 1 bar to about 17 bar, and the same thing may be represented on a pressure enthalpy diagram. So in this diagram also we have this saturated liquid line and the saturated vapor line, and this is the A because we are saying this is a saturated vapor, so it must fall on the saturated vapor line. So here it is A, and what is happening? We are compressing it, we are raising the pressure, okay, and we want to ideally we want to go for isothermal compression. So this is the one, this A to this B is the we are getting. However, in practice we will not be able to get isothermal condition, so we find it will deviate from this isothermal line to this value. So this B prime is the one which will be obtained in practice. Okay. So this is what we are doing, and the ideal work of compression, as we have learnt earlier, that it will be HB minus HA. So the enthalpy over here and the enthalpy over there, this difference will be the ideal work of compression, and generally such a high pressure ratio is obtained by multi-staging the reciprocating compressor or single stage screw compressor or centrifugal compressor. So any of these may be used to raise the pressure from 1 to about 17 bar. And as I said that if in eta IS is the adiabatic efficiency of the compressor, then what we get this particular expression. That means instead of B, we shall be reaching B prime, and this is the kind of expression which is again getting obtained from this expression, that HB prime is equal to HA plus WS by eta IS. Okay. And then we have the compressor power required. This is we can again obtain this simply by multiplying the flow rate of the gas being processed with the actual work done. Okay. For ideal compressor, this one will be unity. Now coming to from point B to C or B prime to C. Now from B prime to C, what we find that we are going from here to here. Okay, we are finding that in this condenser we are condensing the propane, and by condensation what is happening? The heat is being released. Okay, and this heat is released and it is put into the some suitable sink. So that is how we are rejecting the heat from the system, and it is happening at around 38 degrees centigrade. And to take out the heat, to whatever heat is being generated due to condensation of the propane, that is taken out either by the air cooled or water cooled condenser. So we are simply using air or water to take out the heat of condensation from the this propane, and the condenser load is the difference between the enthalpies. Okay, this is quite simple. Then coming from C to D. Now what we are doing after this condensed liquid is being expanded through a jetty valve. Okay, and this expansion is done to about 1 atmosphere, and this jetty valve results in cooling, and this cooling is about minus 40 degree centigrade. Now what happens that in this cooling, here we find that we are getting this particular cooling from C to D, and we are within this particular dome, and here we find we are getting two phases. That means we have liquid as well as vapor. Okay, and we are getting good amount of cooling. This is isenthalpic ideally, and this is what we are writing, that in the absence of heating leak, Hc is equal to Hd. That means this enthalpy over here will be equal to this enthalpy. But if it is not isenthalpic, if there is any kind of heat leak, suppose there is a QL amount of heat leak, then we find this Hd gets raised. The enthalpy will be more than Hc, and this extra amount of energy is coming from the heat leak. And if we want to find out the fraction of the mole liquefied, we can use this particular thing. This is very simple. This is coming from the expression of the overall enthalpy of the system which is obtained from the enthalpies of the saturated vapor and the saturated liquid. So, from that expression which we often use in thermodynamics, we are getting the amount of propane liquefied. So, as I said, because it is there are two phases. So, generally the vapor leaves the chiller. That means we are using a chiller or evaporator. Now, what happens that this this particular thing is this vapor leaves the chiller as assuming that it is saturated vapor. So, HA, because we are going to compress the vapor. So, if we assume it is saturated vapor, then HA will be replacing this HGD, and we are getting the fraction of the fraction liquefied. Okay. Now, from D to A, what we are doing, this is we are evaporating the cold propane in the chiller. Okay. And what is happening that vapor portion cools down to saturated state by the sensible heat transfer. The saturated vapor becomes saturated liquid, and since sensible heat transfer is much smaller than latent heat transfer, what we find the propane temperature remains almost constant. So, even if this two-phase region was there, but even though the vapor will first come to the saturated vapor state from the superheated, then it will be transforming to saturated liquid. And because sensible heat transfer is generally less than the latent heat transfer, it's quite high value. So, we find that we can neglect the sensible heat part, and if you neglect that, we will for practical purposes we take the temperature to be constant, because it is happening at a there is a simple phase change. And we find the propane returns to the compressor suction at slightly above minus 40 degrees centigrade, and heat removed is this HA minus HD. Now, after figuring out all these values, we can easily find out the coefficient of performance of this system, and we find this is QA by WS. We put the values of QA WS, and we find this is COP, and this can also be put in terms of the amount of fraction liquefied. Now, let us see the effect of process variables on refrigeration. First, let us see at the condenser outlet temperature. Now, we find that this condenser outlet is limited by the heat removed in the condenser. How much heat can be removed, that will determine, because we are using either water or air to remove the heat in the condenser. So, it will depend on at what temperature the water is coming or the air is coming, and we know that this particular temperature will dictate the compressor discharge pressure, because it will be, the enthalpy will be dictated by this amount, how much heat is being recovered. And we know that the temperature of the ambient changes from season to season, and also at different point in the day. Okay. So, if there changes, and so will be the temperature of the air will also change, and if they change, then what will happen? It will also change the condensation temperature. So, all these things we will be finding that they will ultimately affect the performance of the refrigeration system. And here in this particular table, we are showing a typical values for the condensation temperature, the change in the compressor duty and change in the condenser duty. So, we find that if the temperature of condensation is changing, we find that how the compressor duty and the condenser duty are changing. Okay, and this is the base value we have considered 30 degrees centigrade, and beyond this is less than 30 degrees centigrade, and this is a higher 30 centigrade. Now, we find that with the change, that we finding that the condenser duty is changing less than the compressor duty. Okay, so that means that it clearly shows that the work requirement changes more than the condenser duty, that is how much heat is rejected. That is why it is important because ultimately we are concerned with the work requirement. So, it is important for us to know the temperature of condensation. And next is the purity of the refrigerant, and because we see that both light and heavy ends may be present, and propane generally contains small amount of ethane, and which may accumulate in the propane receiver, thereby increasing the condensation temperature. Because propane, the ethane will not be condensing at the temperature at which propane will be condensing, because ethane has a lower boiling point, and if it does not condenses, it keeps accumulating. Okay, and it will be as non-condensable. Then what will happen? It will slowly raise the pressure inside the system, and if pressure is getting raised, what will happen? The temperature of condensation will also get affected, and it will also rise. So higher ends like butane, compressor etc. may be present and are removed periodically by heating with hot propane from the compressor discharge. Okay, so we are talking about only the propane refrigerant, and the propane is generated internally from this system only. So that is why it will be containing, it will not be pure propane, it will be having some kind of impurities. So those impurities should be removed before, means ideally should be removed before we carry on this kind of process. Next we do some modifications done. This modification is what is motivation? That compressor work is minimized if heat is removed at the highest temperature from the chiller. This is given by thermodynamics, that the higher the temperature for removing the heat, the less will be the compressor work. And how it's implemented? It is implemented by multi-staging of the compressor to reduce the work per unit amount of refrigeration duty. And this is similar to cascade refrigeration, and this cascade refrigeration we learnt earlier, and the optimum number of stages has to be chosen to maximize the benefit. So how many stages? Because we know that this kind of compression is done in multi-staging, and there will be an optimum number of stages to maximize the benefit of the reduction in the overall this work done. Next we come to stabilization. And why it is done? It is done to recover the lighter hydrocarbons for fuel or sales gas from the liquid byproduct that contain substantial amount of the lighter components. That means whenever we are having the heavier components coming out, with that some lighter components like methane, ethane will also be there. So we do not want to pass this methane with the higher hydrocarbons, because methane will be used as a in the natural gas. So whatever last amount of methane or ethane is remaining, we want to take it out of these higher hydrocarbons. Okay, so that is why what we call it stabilization, and this will also make the storage of liquid easier. Why? Because if we have the lower hydrocarbons, it is difficult to liquefy them. Okay, so that is why, because the lighter hydrocarbons will lower the dew point. Okay, so it will be difficult to liquefy them. So that is why we also need to take out these lighter hydrocarbons to raise the dew point. And if you know that by liquefying it, we can reduce the storage space for a given mass. And in this case, what happens? Feed liquid is passed through a packed bed or a tray column from the top without any reflux. So it is not exactly like distillation. It is more like the stripping section, in which the feed comes from the top and goes out from the bottom, and we are not using any kind of reflux usually. And column pressure is lower than the gas separator to enhance the stripping of the light ends. We know that if we lower the pressure, a kind of flash happens, so that the vapor which is generated by the lowering the pressure, whatever the vapor will contain the lighter components. So the pressure inside the column is kept somewhat lower than the pressure in the gas separator. And if we want to increase the recovery of the light and hydrocarbons, then what we have done, it is passed in stripping gas as well as providing reboiler at the bottom of the column. Okay, so we can put some another stripping gas through the column, which will be again taking out the lighter hydrocarbons from this liquid feed from the top. Okay, it is somewhat like distillation. Again, we are not using any kind of reflux here, so that this kind of stripping gas may be used, or we can also provide a reboiler so that we can boil off the liquid, and by boiling off, the vapor will be enriched with the lighter hydrocarbons. But what happens by doing this, we increase the operating cost of the overall system, because the low pressure stripping gas has to be recompressed if it is to be put back to the inlet gas stream, because once the stripping gas comes out of the system, it will be at a lower pressure, and this stream will not be thrown out, it will be again taken out and it is sent back to the suction side, feed side. Okay, so which has to be recompressed to a pressure which is the same as the pressure of the feed. Okay, so this will again increase the operating cost of the system. So one has to weigh all these things, that whether to whether we are going to increase the operating cost or whether we are going to increase the recovery of the lighter hydrocarbons. So all these things are weighed before designing this kind of system. And here I have shown a demethanizer, which is a part of a stabilizer. Here you can see this is the demethanizer column, actual column, and here we have the inlet gas feed, and here we have the residue feed. The residue gas is coming from the top of the column, and this inlet gas is going inside a coal separator, and we may be using some kind of turbo expander or a JT valve or some kind of heat exchanger to cool it down and sending it from the top. Okay. So it is typically a stripping column with no additional condenser reflux stream. The column diameter increases at the top to accommodate increased vapor feed. You can see the column diameter is more than the rest of this column. Now why? Because as the vapor is being generated, it will need more and more volume. And if we restrict the diameter, what will happen? The pressure drop will rise. Okay. And if the pressure drop rises, we need a compressor to push the gas through. So to keep the pressure drop lower, what we do, that we increase the diameter of the column to handle the higher amount of vapor which is generated during this process. The typical methane content at the bottom is about 0.5 volume % of ethane on a C3 plus free basis. So this is the way we report. It is as a fraction of the ethane that is present in the gas in the bottom product. And feed may be from turbo expander, JT valve or heat exchanger. This turbo expander, JT valve or the heat exchanger I was telling you. The pressure and temperature at the top is about 14 to 28 bar gauge and about minus 115 to minus 110 degrees centigrade. So you can see it is quite low pressure. Okay. And there are multiple liquid feeds that come from low temperature separators. So there are multiple feeds. We have this one feed, second feed and third feed. So there are multiple feeds. They are coming to the system, and multiple side boilers are used. Like here we have the multiple side boilers, and why they are used? So that we can recover some of the refrigeration available in warming of the NGL system. And here are some books which you can refer to for further clarifications. Thank you.